for making the time today. Thanks for the chance to come and talk about this. So we're going to talk about data structures and algorithms and big O notation. In a minute, I'll tell you a bit more about why this topic is interesting to me and why what I want to communicate to you about it. So I guess just to start, I'll introduce myself. My name is Adam. I work at a company called Citadel. We're a hedge fund. We're about 3,000 people, some of whom are analysts who are working with markets and market data. Many of us are technologists, and so I work closely basically with a team that does data science type stuff, trying to help them acquire data, create models that use that data, publish visualizations about that data, and then ultimately trade in the markets with that data. And then kind of over the course of my career, I started out as a technologist working in a company similar to the one that I'm in now. And then I spent a number of years where actually I wasn't doing technology at all, but I continued on in the commodities trading space. Still like a very data intensive analytical job, but I didn't use technology anywhere near to the extent that people do in the markets today or that I do now. And then a couple of years ago, I came back to technology as a focus. Basically realized I enjoyed building things and solving technical problems much more than I did, watching my positions go for me or against me, mostly against me in the market. And so, a couple of years ago, I started from a place where I hadn't spent much time working with technology in a number of years. And so I had a lot of work to do getting caught up in things that had changed in the technology space, all sorts of new programming languages, new databases, other new technologies. Cloud computing wasn't a thing, when I came out of school, but was kind of the dominant thing. And so, I spent a couple of years, pretty deeply immersed in teaching myself everything that I could about, software development and, digital technology. And one of the things that I fell back on, I had the very, very good fortune of having a degree in computer science from MIT. If you're going to have a degree in the discipline, that's one of the good ones to get. And I found that I had a pretty strong, core in the fundamentals in computer science, with a lot of that referring to what we're talking about today, data structures and algorithms. And that created a lot of flexibility for me in making a big change in my career and getting acclimated to a lot of change in technology. And now in my role, I spend a lot of time interviewing other candidates. I spend a lot of time designing systems, and I still lean very much on that skill set in data structures and algorithms. Data structures and algorithms are a big, big, big part of how we evaluate candidates, coming into our firm. And this is as true in my job now as it was in the last several jobs. And so, I understand that, some of you have computer science degrees. Some of you have studied this on your own. Some of you are maybe coming to this material for the first time, but that you're all sort of early in your path as technologists. And so, what I really want to do today is I'm not qualified in the span of 1 hour to turn you into deep, deep experts in data structures and algorithms. But what I can do is kind of give you the lay of the land. I can point out, what are some of the particular bits of knowledge that I keep coming back to? What are the skills that we develop around it that are useful, and how I apply those skills in my work as a technologist, and how we kind of apply those skills as well when it comes to getting a job and kind of validating that you have this skill set. And at the end, I'll conclude with a couple of resources that you can use to kind of continue the course of study. I have a lot of slides here. They're not as polished as I would like them to be, and it might seem to move a little fast. So I think I'm going to talk for another 40 minutes or so, and then we'll turn it over for questions. But everyone should feel free to reach out anytime if you have any further questions on this stuff. If you want to talk shop, I'm very happy to do it. I'm here to help you level up. So with that, let's talk about, what is the knowledge base that we're talking about when we talk about data structures and algorithms and big O notation. And kind of, I'll take this backwards. I'll start with, big O notation. And so here's kind of like the key question that we're addressing with all of the things that we're going to discuss today. Anytime you're building a system, it takes in a certain amount of data, or it's operating on a certain set of records, or you've got a certain number of users, right? So call that number of users or that quantity of data, call that n. So as n grows, and if you're building a platform for public use, you sort of hope that it will grow. Or perhaps if you're not building something for public use, if you're in a team that's growing over time, if you're ingesting more data, a really important question to ask is, as the problem size grows, what happens to the resources that it takes to solve that problem? And when I say resources, I could mean just the time, the compute time to get an answer to something. Could mean the amount of memory that it takes up. Could mean the number of servers that are required to process the workload. It could even mean something like how many calls to the database or some external API that maybe you get charged for. And so then you're very, in all of these cases, it's some resource that equates to some limitation on your ability to solve the problem. And so you kind of want to plan to make sure that you can solve the problem in a way that economizes on the resources. So big O notation is the language that we use to talk about this. And we can talk about the formal definition of what big O means if you like, but the key thing to take away is that if I say something is order of n squared, we're describing the characteristic shape of the way that it grows as n grows. So if something is order n, that means if we 10x the data we're putting through the system, we're 10xing the runtime. If it's order n squared, if we 10x the amount of data that we're processing, we're 100xing the runtime, right? Likewise, if it's log n, if we 10x the amount of data, well, actually, then in that case, we're only 3xing the processing time. So what's important to note is when we use the big O notation, it's as important to note what it describes as what it intentionally leaves out. So when we say something is order n squared, if I were to come up with a mathematical function that said for a size n, how long does this code take to run? And that function is n squared plus 3n plus 22 or whatever it is. When I say order of n squared, what I mean is that in that function, the big deal is the n squared part. That the n doesn't matter, the 22 doesn't matter. Even if it's 3n squared, the 3 doesn't matter. So we have what we call lower order terms, the things that don't drive the shape of the growth as much as what we describe with the big O notation. And we have these constant factors, which are an important part of the detail. And to be sure, in a lot of applications, the constant factor is kind of the determinant of whether something is fast or too slow. But the thing that really drives the shape of the growth, the thing that really kind of matters if you want to forecast how are things going to evolve as you grow the size of your system, that's the thing that's in the big O notation. And it's a structural property of a process. So we'll look at some different algorithms, different data structures. The big, the function that we ascribe to it, the big O notation, is based on something about that process that isn't going to change. It's sort of fundamental to the approach that we've taken. So even if we find a faster processor to run it on top of, or we come up with a better compression algorithm or something, the shape of the problem isn't going to change. And so one thought exercise that's kind of useful for understanding the role that this plays when we're building systems. If you're building an application, there are a lot of different parts to it. Different pieces are actually going to have like these different growth characteristics. So one thing that I thought was interesting, I'm not a biologist, but it was explained to me that if you took a mouse and you expanded it to the size of an elephant, it would actually collapse under the weight of its own flesh, which is kind of a weird and grotesque thing to think about, but it speaks to a mathematical truth that's really relevant to us as software developers. The reason for this is that the strength of an animal's bones are a function of the cross-section of those bones, right? So they're a function of an area. So if we double the dimensions of a bone, we're going to quadruple the cross-section, right? If it's squared, so 2 times 2 is 4. The weight is a function of the volume, right? So that's the cube of it. So if we double the dimensions, that's 2 times 2 times 2, we're actually 8xing the weight. And so if you have, something like an animal, like a living organism, it's a carefully balanced system. and you scale the different parts with different orders of growth, even though you're kind of applying the same, scalar change to the dimensions, when some parts grow at the rate of, n cubed, and some parts grow at the rate of n squared, things can very quickly come out of balance. So kind of the baseline in this space is, order n, linear time. And this is, the baseline because basically if I give you some data that you've never seen before, without anyone having done any prior processing, if it's just raw data, you've kind of got to look at everything in that data set before you can do anything fancier, right? And so that means, if there are n items in the collection, you've got to do n operations to touch everything in the collection, right? If, we're not doing anything where we're relating different, subsets of the collection to one another, we don't have like any special lookup structure we can use to kind of speed up the workload. So, order n is, kind of the baseline expectation you have for processing anything. If you're, doing better than that, then that's great. If it's, super linear, which we'll get into in a second, then you've got to, start getting smart. And again, kind of going back to this slide, we've got, in the middle of the yellow zone, order n is kind of like that linear baseline. So again, we call this linear time. It's the amount of time that it takes is linear in the amount of data that we're handling. So then there's a whole class of operations which we'll call superlinear. And that doesn't mean that they're very, very linear. That means they're above linear. And so the most benign case of this is when something is order n log n. So that's n times the log of n. All right, and we'll look at sorting collections in a moment, but basically this is kind of like the typical minimum time to sort something. It's a little more than linear, but it's not quite the next category, which is quadratic time, order n squared. And this is what you might expect if you've got n items and you have something to do where you've got to look at every pair of items, right? In n squared, or sorry, among n items, you're going to have n times n minus 1 divided by 2 possible pairs, right? For each item, you can pair it with one other item that's not itself, and half the time you're going to be coming up with a pair that you already came up with. So that's n times n minus 1 over 2. And again, like we said before, you take n times n minus 1 over 2, that's n squared minus n over 2. We don't care about the n term, and we don't care about the 1/2 on n. It's still order n squared. And so we call this quadratic time. And you'll know you're looking at something that's quadratic time in your code if you see, nested for loop, and each loop is looping over the same collection. So to pause right here, if something's linear time, it's order n. If we 10x the amount of data in the collection, we're going to 10x the runtime of the algorithm. If something's n log n, we 10x the amount of data, we're going to 30x the runtime of the algorithm. If something's order n squared and we 10x the amount of data, we're actually 100xing the runtime. And I'm going to go down the list here, but it only kind of gets worse from here. So we have another class of runtimes that we call polynomial time, and that's n raised to any other exponent. And again, this is more kind of nested looping. Anything up to polynomial time is kind of considered manageable. It could be, if you're dealing with like a large exponent, it's, it can get expensive pretty quickly, but these problems are still considered, generally solvable in computer science. The next class is if we get to, exponential time, right? Something that's like 2 to the n. So let's say I have n different Boolean flags and I need to test every different configuration of those. If n gets very large, then the total number of combinations that I have to evaluate explodes. And so an algorithm that's going to require me to test each of those is ultimately not going to be tractable if I have a large n. This goes even more so for things that are factorial time, right? And order n factorial, where we're looking at all the different combinations of n different items. And just kind of maybe to make this a little bit more concrete, let's say we have a list of addresses. If I want to find all of the addresses in Minnesota, I can process that list and order n time, scan each one, grab all the ones that are in Minnesota, and we're good. All right. If I want to find all pairs of houses that are within 10 miles of one another, that's order n squared. I've got to iterate over every every house. For each house, I iterate each over every other house and test whether they're, you know, within 5 miles of each other, whatever I said. If I want to start doing something like figure out what is the shortest path I can take that touches each of those houses, you know, that becomes one of the classical problems in computer science that there isn't a known solution for, the traveling salesman problem. Then we're looking at something in factorial time, right? So that's the superlinear side of things. That's where generally either you're doing something not as well as you could, or you've got something that's just like inherently expensive to figure out. So now we've got this class of things that we call sublinear time. And these are generally achievable if we've had the opportunity to look at the data already. We've had the chance to arrange it into some sort of structure, you know, that we can use to operate on it more efficiently. So, you know, the first of these is, you know, just plain log n, logarithmic time. We'll look in a few minutes at like a tree data structure, or we'll look at binary search. These are solutions where you can take the collection, you can slice it in half, operate on, you know, just a piece of the collection, slice it in half again, and keep slicing it in half. And that, you know, that subsequent halving is, you know, gives you this logarithmic behavior. This means that, you know, you can double the size of your collection, but you've only added one additional step to your processing. And so you can grow your collection quite a bit, and the cost of processing your collection grows rather more slowly. Then we get to kind of like the holy grail, which is constant time. Any operation where you can, you know, the cost to operate doesn't vary as the collection grows. And this is where the magic happens. This is really valuable stuff. And this is, you know, where like you go into Google and you punch in a search query. The internet is many millions or billions of times what it was when Google started 20 years ago, but it doesn't take billions of times longer to complete your query. I'll touch on amortized constant time a little bit later. So now we kind of get into the question of how does the right choice of an algorithm drive performance or scalability as we're, you know, navigating these different orders of growth. So kind of the classical starting point for algorithms is to look at sorting a collection. Maybe it's just a list of integers. So, you know, if I set you down and I didn't really challenge you to come up with the fastest possible sorting algorithm, you'd probably write, you know, the same one that I did the first time that I sat down to do it. You know, kind of, you know, what we'll call the naive or straightforward approach, which is known as selection sort. And it turns out that this is an order n squared solution, and we'll talk about why that is in a moment. But it's pretty simple. You've got a list of n integers, and you know, okay, first I need to place the smallest element of the collection. So I loop over the whole list of n integers. I find the smallest. I put it in the first place. I swap it with, you know, whatever was there. And now I repeat the process for items, you know, 2 through n. And I do this n times. And on average, it takes, you know, n over 2 times to loop through the whole collection, right? The first time takes, I've got to loop over n items. The last time I've only got to check 1 item. I'm doing this n times, you know, so n times n over 2. It's, you know, order n squared. So this is, you know, pretty straightforward. It makes a lot of sense. I think it's a pretty sensible approach. It's pretty easy to comprehend. The code for it, if I, you know, wrote it up here, would also be pretty easy to follow. Seems reasonable, but, you know, we just discussed how quadratic time is kind of not ideal. So here's another approach that turns out to be about as good as the best approach that you can get, you know, for a really general sorting case, which we call merge sort. And when I describe this, it's going to sound like a little counterintuitive. It might even sound like no way that this is as simple or any way faster than, you know, the selection sort. But let's look at this for a minute. So the idea is we've got n items. What I can do is I can take that collection of n items and I can split it in half. And each half, I can sort that. And we'll defer for a moment the question of how I do that. Let's assume now that I have 2 halves of the list and they're both in order. Well, it's now an order n process to go over the 2 halves of the list. You can think about it as though I wrote them down on 2 pieces of paper side by side. I put a finger on each, you know, piece of paper, and I go down the list, and whichever side has the smallest item next, I take that item, and I keep going until I've gotten everything off of both lists. That's an order n process, and I can very easily take two sorted lists and turn them into one sorted list in order n time. So the question is, how many times do I have to do that, and at what point do I have a sorted list? Well, it turns out if you keep having your list, eventually you're going to end up with a list that has only one item in it, and that's very easy to sort because it's already sorted. So if you combine two lists that have one item, and so on and so forth, then you get to, you have, order log n steps that you've got to slice your list into. Each one takes, order n time. So n times log n, you've got order n log n to sort the whole shebang. And it sounds like it shouldn't work. It sounds complicated. It sounds like it shouldn't be any faster than the selection sort approach. But here's a visualization of it. And actually later in the deck, I'll link you to the article that this came from. But you can see here that there's actually quite a number of items in this collection. And yet this whole thing got sorted in only about, I think it's 7 steps. And at first I thought this might be glossing over and skipping some of the steps. But if you really look closely, you can see actually that's all it took to sort this thing, was like kind of these 7 passes through the list. And so that's pretty powerful stuff, that log n, logarithmic processing there. And so if we look at that, if we compare, order n squared to order n log n, what does that really mean for collections of different sizes, right? So if n is 10, selection sort is going to take, call it 100 units of time to run. Order n log n, 10 log 10, you're talking about 23 iterations, 23 units of time. So already we're kind of ahead by a factor of 4. If n is 1,000, 1,000 squared is 1,000,000 units of time. 1,000 log 1,000, well, we're just talking about under 7,000 units of time. So we're already kind of coming out pretty far ahead. If n is 1,000,000, and if it's not hard to imagine applications where you're handling 1,000,000 documents, 1,000,000 users, whatever, we're looking at 1,000,000,000,000 units of time in the n squared formulation. If we're looking at n log n, we're looking at just under 14 million units of time, which is nothing to sneeze at, but it's a lot better than 1,000,000,000,000, right? It's like an 80,000x speed up. So to me, this what's interesting about this illustration is that even for something that seems like sort of counterintuitive, that it would be an improvement over the most obvious approach, like ultimately, like this big O characteristic, right? This like asymptotic behavior, as we call it, ultimately wins out in a very big way. It ends up being very, very impactful in the overall performance of something that we built, right? And if you think about like we're talking about a trillion units of time versus 14 million units of time. You think about if you're spending money that corresponds to that amount of time, or a user is waiting for 1 trillion seconds versus 14 million seconds, or whatever it is, that makes a very, very big difference in the success of what you built, ultimately just because of math. So kind of the next like port of call in when you're learning algorithms is searching through a collection. And so again, kind of just going with a list of numbers, if we couldn't make any guarantees about the state of that list of numbers, if I had to find, that needle in the haystack, we're talking about something order n, right? I look at every item in the collection and I keep going until I find the thing that matches what I'm looking for. And, on average, we're going to look at, half of the items, so n over 2. But again, if we 10x the amount of items, we're 10xing the amount of time it takes to find something. So that's kind of not ideal. What we find, though, is that if the collection is sorted, then a whole new category of approach becomes available to us, and we call this binary search. And, this, like a lot of the diagrams in this presentation, I've pretty much just stolen from Wikipedia and the web, and I'll try to attribute where I can. But so the idea here is, if your list is sorted, then there's a trick that's available to you. If let's say in this list of integers, if I'm looking for 6, I know the dimensions of my list, so I can find the thing that's exactly in the middle. And in this case, it's 4. So now that allows me to cut the problem in half, right? I know it's sorted. So if 6 is greater than 4, it's in the back half of the list. If it's less than 4, it's in the front half. So I know I'm searching the back half. I now just repeat the process again. I look between, you know, the middle of the list and the end of the list, and I pick a point in the middle, and I say, okay, is it greater or less than this midpoint, this pivot? And here we pick 7, we know it's less, and so we're able to find the 6. This is a pretty small problem, but it's pretty illustrative. You know, again, we're looking at something that's logarithmic time because we're successively slicing the problem in half. So even very large problems, you know, as the size of the problem grows, the runtime does not grow quite as fast. And then, you know, kind of the other point that I want to make about this is that just knowing that this list was sorted, again, opens up a whole new category of approaches. And this is a thing that's going to come up again and again throughout, you know, data structures and algorithms is, you know, is there an assumption that you can make about your data, or is there a guarantee that you're given about it? And when you have that information, how does that change the approaches that are available to you, for better or for worse? So from here on out, I'm going to kind of just stomp through what are some like the main data structures that I think about or use on a day-to-day basis, and some of the important things to take away about them. The field of data structures and algorithms, you know, again, is deep and rich and wide, and you know, you can get 7 PhDs studying it. We're not going to cover all of that, but there are a few things that seem to come up again and again and again, you know, or represent concepts that I think are useful. And so one thing that I think is useful is looking at, you know, one thing that's common all the time, we've already talked about it a number of times, is just a list, a simple list, an ordered collection of some items. And there's two, you know, really basic ways to represent that. One is an array, right? And so, you know, if you've worked with a language like Java, often in like JavaScript, any, you know, C, any low-level language, you're dealing with an array, right? It's a fixed list. Or sorry, it's a fixed range of items, you know, and they're all of, you know, a given type. And a couple of things stand out about this. Number one is, you know, it's static, right? It's got to be of a fixed size. It's got to be of, you know, some uniform type. And it has kind of this implicit structure. That's sort of why it works. You know, it all boils down to ultimately how, you know, data is represented in a computer, right? You know, in memory, you have just, you know, a contiguous list of cells basically that can contain data. And you know that if your data is of uniform size and it starts at a specific point and it runs for a specific, you know, number of items, that I can come up with an index. I can say, okay, if I have, you know, space for 10 items, I know that, you know, the array starts at memory location XYZ. If I want to find the third item in the collection, I don't have to do any searching to find that item. I can just do some math based on what I know about the size of the item, the index, and where it starts, right? And so we get constant time access to anything, you know, random access anywhere within this array. And that turns out, you know, it's sort of constraining in the sense that the size of the array can't change, right? That the types can't really vary. But at the same time, it also gives you a lot of leverage in the sense that you can access things in there very, very fast. You have a lot of certainty about the structure of that. There's no searching. By contrast, we have this thing called a linked list. And again, it's, you know, it represents like an ordered collection of things, and it consists of a number of, you know, records, let's say. And the record could include some data. It could be, you know, like information about a user. It could be a string. It could be a number. Part of the record is some sort of reference, right? It could be an address in memory. It could be some, you know, record identifier in a database, but it's some reference to the next item. And generally assume that we can use that reference and in constant time find that next item, right? Typically just looking something up in memory. So what are the advantages and disadvantages of this approach over the array? Well, the advantage is that it's dynamic, right? It's, you know, you can, you know, as long as you can allocate these records in memory, you can kind of place them wherever you want. They can point to each other in the right order. You can, you know, find something in the middle, disconnect 2 nodes, put another one in, connect it, and you've expanded your collection. You can find something and delete it, right? You can take one reference that points to an element of your linked list and point it to the next element instead and get rid of the one that you just skipped over. Now you've shrunk your list. So that's also really powerful. You know, but again, you kind of lose that benefit of having that random access because you kind of have to search through the list to find where the items are. You don't have the same sort of certainty that you do with an array. This type of linked list, there's also a variant where an item not only points to the next element in the collection, but it points to the last one as well. And that opens up a couple of other interesting possibilities. We'll come back to these in a minute. So, then there's also stacks and queues, which are kind of at their core are also lists. And the underlying implementation of these, can be either an array or a linked list or something else, right? The stack, if you talk about like the call stack in, in any language you might be using, that's pretty similar to a linked list in its underlying implementation. And the idea of a stack is that it's a list that you push things onto and pop things off of. And I put a picture of a stack of pancakes here because it is kind of like a stack of pancakes in the sense that, the top of the stack of pancakes, that's the last pancake that was put on. That's also the first one that's going to get eaten, unless, of course, you're slicing all the way through the stack. But if you're like me, you kind of work your way down. And we call this, last in, first out, or LIFO. And again, I said that this is kind of something you would see in a call stack. A data structure like this is used in all sorts of things where you're processing call graphs, like distributed tracing and microservices, and processing a call stack in an interpreted language like Python. Similarly, if you're parsing something, right? If you're looking at like nested parentheses, a stack is kind of a useful structure for looking at these sorts of things and kind of figuring out which stage of the process you're in. You could take the same underlying implementation and just sort of change the semantics, and you get a different, we'll call it a data structure called a queue, right? And this should be familiar to anyone who's ever stood online for something. Something's first come, first serve. We call this first in, first out, right? You're the first person in line. You're the first person into the movie theater back when that was a thing, right? And you see queues all over the place, right? Very often it's used to manage a workload in a distributed system. People will push things onto a queue for processing elsewhere. So trees and heaps are another very useful category of data structure. And we talked about binary search. And this kind of takes, the leverage that we got from that kind of logarithmic processing of stuff and renders it out as a data structure, right? In the binary search example we looked at, we were kind of successively slicing up a list and handling it that way. If we take kind of the same ideas of like a linked list where you've got a node or a record that has pointers to other records, then you can create a structure that looks like a binary tree and kind of simplifies some of the things that we were doing in the binary search, right? So in this example, basically every record has two pointers, one to something. Every record has a value, we'll call that a key, and it has two pointers, one to everything that's less than that key and everything that's greater than that key. So in this example, kind of our root node is a 6, and its less than key, pointer points to a tree that's rooted at 3, right? And that in turn, on the less than side points to 1, on the greater than side points to 5. So if, in this tree, if you were looking to find the record with the key 5, you would look at 6, you'd know you need to traverse down the lesser side. That would bring you to 3. You'd know your key is greater than 3, so you've got to traverse down the greater than side, and that, that would ultimately bring you to 5. And again, because you're slashing the problem space in half every time, you get this logarithmic performance benefit. So even for, very, very many records, you only have log n steps that you've got to go through to find what you're looking for. And it turns out that this is actually used in a lot of database indices if you're database inclined. Kind of a variant on this, it sort of turns it on its side, is a heap. There are max heaps and min heaps. It's similarly structured in that it's a tree. It kind of makes different guarantees about the relationship between a parent and its children. I have pretty rare occasion to use this one, but it's one that comes up. It's pretty good if you need to maintain a prioritized list where you need to find, the item in a collection that has the greatest key or the least key. But you still are in for like that, logarithmic time work to keep this this data structure updated. So both of these are sort of logarithmic time access processes. So here's one that I was kind of hoping to have time to go into a bit more detail on, because I use this one several, 1,000 times a day. You probably do as well. But the hash table is an extremely valuable, extremely magical data structure that has a lot of complexity that most of us get to take for granted because the implementation is baked into, if you're using Python or JavaScript, it's already baked into the runtime, or maybe there's like a standard library implementation for it if you're using Java or C++. But we talked about how with an array, you get this, random access benefit. With a linked list, you get kind of this dynamic benefit. So what does a hash table do? A hash table can also be called an associative array. And the idea is that you have data, that are your keys and your values. And you get to, associate a key with a value. And for a given key, you can set the value, or you can look it up in what we'll call constant time. In a second, we'll get into why it's not exactly constant time, but in practice, for the most part, it might as well be constant time. And the idea, the magic that makes this possible is that you begin by allocating an array. And the array is going to consist of various records. Each record is going to be effectively a linked list. And you're going to have something that we're going to call a hash function, because it is a hash function. And if you want to go get your PhD on just writing good hash functions, you can go do that. But what a hash function will do is it'll take some piece of data and it'll convert it into a number. And that number may be equal to or many times greater than the size of the array in the hash table. But the idea is that we can take that data and map it to the number. And the same data gets you the same number every time. You can take the data, you map it to the number. You map the number to an index in this array of buckets or of linked lists. And then if I want to associate, in this case with, call it with Sam Doe, I come up with his hash code, right? It's 254. I take the name Sam Doe, put it into my hash function. I get the index 254. I now can look up in the table, in the bucket, I can have an entry that says Sam Doe's phone number is 521-5030, right? Periodically, though, even in a well-designed hash function, you'll get what we call a hash collision, where two pieces of data that are otherwise distinct, go into the hash function and they both come out with the same hash code, or they come out with different hash codes that somehow map to the same bucket index. And now we've got like this linked list of every item in the hash table that map to that index. And what we now do is we search through the list of things in that bucket, and we find the thing that matches the key that we're looking for. So if we choose the right hash function, if we choose the right number of buckets, then in practice, these linked lists tend not to be too deep, tend not to really grow too much with the size of the collection that we're storing in the hash table. Or if they do, we can do what's called a rehash and kind of realign the data structure, but we can still get what we call amortized constant time, where basically in the average case, you've just got the time it takes to generate the hash code, the time to look it up to look up the right bucket, and then a very short traversal of that bucket to find the data that you're looking for. And this is really powerful, again, because you can work with very large collections of data and still get very fast performance, looking things up, storing things. And especially when you use this in conjunction with other data structures, you can get very performant solutions to a wide range of problems. So I'm just gonna give shout outs to some other data structures that that come up that I use. Again, there's a deep, wild world of data structures out there, and you should always find the one that's relevant to the use case that you're working on. But ones that come up again and again for me are directed acyclic graphs. These come up all the time if you're building a data pipeline or you're trying to plan out work that involves different tasks that have dependencies on one another. Another one that I find useful is a trie. I think sometimes it gets called a suffix tree. That's another useful lookup data structure. And then a very, very rich domain of data structures and algorithms is graphs. There's a lot of problems that can be represented as graphs. There are different ways to represent a graph. You can represent it as a matrix. You can represent it as a list of different items and the relationships they have to one another. Social network is a great example of a graph and a graph problem. like navigation, like mapping, is also another good example. So I'm going to try to breeze through the next couple of slides to be able to take some questions, but we're getting into some of the things that I really want to communicate to you about. What do you get out of working with data structures and algorithms, and what's important as you work on these things. So in addition to like the raw knowledge that you'll have about the data structures and the algorithms that you get by studying them, there's some skills that you develop by working with them or in working with them that are really relevant. And those are, I'll go through each of these one by one, but working with orders of growth, which we started off with, pattern matching, which is kind of a general thing across all engineering, and likewise for trade-offs. So, all of this is kind of in response to the question of what makes data structures and algorithms a fundamental skill that, that gets emphasized so much. So working with orders of growth is kind of a key thing, right? It's important to be able to write a piece of code and then look at it and then answer this question that we've been asking, right? If I throw 10 times as much data at it, is it going to take 10 times as long to run? Is it going to take 100 times as long to run? Is it going to take 30 times as long to run? What's it going to do, right? And so, eventually, as you work with data structures, as you implement them, you'll learn to identify these patterns in your own code, in other people's code, in other systems. You'll identify patterns for how to change, what is the order of growth of a given piece of code. And it's important because when you're building a system, often you'll work with, an experimental set of data or some toy data that you've built by hand. Your computer is very, very fast. And so, even decent sized data sets, you can do a very naive implementation of something, right? Like our selection sort, and it's going to run fast enough that you're not going to notice if it's slow or care if it is. But again, if you're building for a growing market or a growing use case, very quickly you're going to find that your system is going to outgrow your vision for it. So understanding the consequences of the choices you've made, understanding how to mitigate those consequences, very, very fundamental skill in engineering, especially when you're thinking about, again, taking a mouse and growing it to the size of an elephant, right? When you have different parts of your system that grow at different rates given different changes, how can you manage that? How can you stay on top of it, and what measures can you take? And that kind of gets into this, behavior of composed systems. This knowledge about orders of growth and data structures and algorithms, it doesn't only apply to your own code, code that you're going to write or maintain. This is a factor in the behavior of, databases that you use, libraries that you use, APIs that you call. So I put the logos for Postgres and Redis on here because I've spent, for things that I've worked on, I've dug into their documentation, and, they'll explain to you like we talked about like the big O notation for how, the time cost for different operations that they offer, right? If you're using a SQL database like Postgres, eventually you're going to need, to do something about the performance. One of the things that you'll typically do is add an index to a database collection. And what is an index but a data structure very similar to the ones that we've just discussed, and it's going to offer you performance characteristics similar to what we just discussed. So, again, like understanding how a binary search tree works doesn't just explain to you how you might use a binary search tree in your code. It also explains to you, what is a database like Postgres doing under the hood. So it's a valuable skill to acquire in using other systems as well. Likewise, knowing and applying data structures is just one case of, all across technology, all across your work as a technologist, where you're going to be pattern matching. And this is true for, object-oriented design patterns, systems architecture patterns, coding style and macros. You're going to be faced with new problems every day, but they're only going to be, 90% new. There's going to be a lot of every problem that you're looking at where there's some known off-the-shelf solution. And so, either, you can take an actual existing solution and apply it to your situation. Likewise, if you're building something new, but it's kind of, in the shape of something else that's pre-existing, that's well understood, it'll help you communicate to other engineers if you say, oh yeah, I implemented a binary search tree here, or I implemented binary search here, rather than saying, well, first what I did was I sliced the list in half. Then it becomes an idiom that you can use to communicate with other engineers that you're working with. Likewise, when you start to think of these things in terms of patterns, kind of like we explained with how the the hash table works. You can sort of use the patterns together to create novel solutions. Another important thing, as you study these data structures, why very similar data structures exist, or when and how to use different ones, is you start to think about and study trade-offs, right? And that is so much of our life as engineers and as developers, is understanding the different costs and considerations and benefits in building something, and how do we make decisions that favor what's important to us at the expense of what we care less about. So a good example is space versus time, right? This is one that comes up again and again. You will often have the choice to take an approach where you're using up more space in order to make something faster, or you're making something slower in order to have it take up less time. And so a second ago, we talked about, graph representation, right? That's if we have like a list of entities and we have relationships among those. There may or may not be a relationship between any two items. There might be some data associated with that. We kind of have two ways to go about that, right? One is, I said the matrix representation. So the idea is if you have n items, you have, an n by n grid, and in every cell of that, you put the data relevant to the relationship there. Turns out that takes, n squared space, but for any two items in constant time, you can look up what is the data relevant to their relationship. If you have a very dense matrix where you're using up a lot of that space, that's a good trade-off. If it's very sparse, if a lot of those entries in the matrix are empty, you're wasting a lot of space for a little bit of a time benefit. But likewise, if it's a sparse matrix, maybe one thing you'll do is, instead of populating the full matrix, you'll just have a list for node A, I have a relationship with B and C, and here's the data. And then you've got a little bit more searching to do to find the relationship between any two items, but you're taking up a lot less space. So that's one thing. Another one is read versus write. You're going to have, different workloads. Sometimes you have something where you're writing every so often, but you're reading constantly, or maybe or maybe the opposite, right? Maybe you need to write a lot of data, and then you're querying it very sporadically. So there are some things like, a binary tree lookups are very, very fast, right? It's only log n. But maybe, you're writing so much that, the log n insertion time is too much. So it might be worth, just having an append only log, right? Where you're just writing, adding to the end of your list, and you have some order n process where you're scanning things when you need to read, because you are reading very infrequently, but you need your writes to be fast. Other things to think about, like speed versus accuracy. There are a lot of algorithms where you can get an approximate answer very fast, or you can get a very precise answer very slow, and you need to think about that as well. Another aspect of this, kind of where we talked about where, how you can search for things faster when the list is sorted. It's assumptions and constraints. Different data structures, different algorithms kind of, come with like a preamble, like only use this if your data is X, Y, Z. When you know something about the problem space, maybe you have a different set of solutions that are available to you. Or maybe you can tell your users, well, actually, if you restrict your name to 32 characters, then I can make, the lookup of your record that much faster. A good example of this is we talked about how like sorting things, order n log n. If you're sorting a list of alphabetical letters, right, then you can actually do that in order log n time. Because you can go over everything in the list and just count up each, the number of occurrences of each letter, and then you can iterate over that count and then re-render the list in sorted form again, in order n time. So really quickly, data structures in your career. Number one, for doing the job. I don't know how to make it any more plain. Understanding data structures and algorithms is key to building solutions that are performant and that are scalable. Building it in the first place, understanding, I used an order n algorithm, we can take 10x the load and we're going to be fine. Or this is like an order log n algorithm, we can take, 100x the load and we're going to be fine. Or I had to cut corners, I built this with a quadratic time algorithm. If we get 10x the load, we're really in trouble. That's a valuable thing to know before it happens. Also when you're building something innovative, when you're kind of, working in uncharted territory, having this body of knowledge to work with, these are first principles. You can go back to them and kind of reason about, what is going to be the approach that's going to help me to achieve something truly novel. Likewise, these provide a language, as I said, like patterns and so forth, that you can use as a common frame of reference with other engineers. Likewise, if you know your data structures well, you know your algorithms well, you know when a stakeholder is confronting you with a problem and maybe some performance expectations that just aren't realistic, right? If they're asking you to find the shortest possible path through a list of cities, you know that they're hitting you with a problem that if you could solve it, you would need to waste your time working with them. You'd be a billionaire sitting on a Turing medal. Having a root in these fundamentals helps you approach a new problem, and it gives you your bearings in dealing with it. When you approach new technologies, they're subject to these same, constraints on growth, these same sort of patterns as you're going to encounter building, a binary search tree, in your editor on your own. So this kind of gives you a way to approach it. Lastly, this stuff plays a role in actually getting a job, right? Data structures and algorithms, we test for them a lot when we're interviewing people. There's debate on Twitter, is this a good way to screen candidates? I've had candidates ask me, well, at Citadel, do you sit around implementing binary trees all day? No, we use existing implementations, but there are a number of ways that this is valuable, right? It sort of tests for the skills that we just discussed. Again, like part of the debate is this gatekeeping? Are these, is this a way that people who've gone to, quote unquote, the right schools kind of test for other people who've gone to the right schools? I think there's certainly people who approach it that way, but I know that I found enough valid use for these skill sets and the things, again, the skills around it in my work, that I want to know that someone that I'm working with, has also invested the time. It doesn't have to have been at, a good school. It can be, on Wikipedia, but that they've taken the time to understand this stuff and that it becomes a part of how they think about and evaluate their work, and honestly about how they think about and evaluate my work. How they can, hold me to a higher standard, how they can give me advice on what I can be doing better. Things like your colleagues are going to have a lot of different skills and abilities that are going to be relevant to how they work with you, like their coding style and so forth. But there's a lot of subjectivity in assessing those. And so, you can more objectively measure in the space of an interview. Does someone know data structures? Can they reason well about, the asymptotic time, runtime of their algorithm? Those are things that can actually objectively happen or not happen in an interview. And so they're good things to engage in that process. And again, I think, like I said, these fundamentals kind of help you adapt to new problems, new projects, new technologies. And so when someone's, got a strong basis in those fundamentals, then you can trust that maybe you're hiring a Python developer, someone's coming to you as a strong JavaScript developer, but they know their data structures really well. They can implement them. They can reason about their code. That it's just a matter of them sitting with Python long enough and applying those same skills, and they're going to be really effective. So I'll send out this deck. Here's links to a couple of resources that you can use to study further. Wikipedia has a lot of articles, a lot of good articles about different data structures, different algorithms, references to papers, and so forth. Ditto for Wolfram Math World has some useful stuff. I liked Visualizing Algorithms, which is kind of like a neat visual essay that actually has some graphics and animations that explain sorting algorithms in addition to some others. I linked MIT OpenCourseWare and their algorithms course. I think, there are tons of online courses, that are public or that are through like Coursera and things like that. I think finding one that, agrees with you and working through it is great. I linked algorist.com. So this photo here is of my recommended book on the subject, which is The Algorithm Design Manual by Steve Skeena. And what I like about this one, compared to a lot of other books on the topic, it's more practically oriented. It's, kind of short and succinct about, with sample code about, implementing like kind of the key data structures and algorithms, but it's also got a lot of stories that kind of motivate, how the right choice of algorithm for a given problem can create an impactful result, for your users. And one of the ways that I got to this book was through a blog post by a guy named Steve Yegi about interviewing in general. He's got a little bit in there about algorithms interviews in particular, just kind of in general a good read when you find yourself on the job market. And then lastly, I linked a video on YouTube sorting out sorting. And when I was like in junior high at nerd camp, this was the video that they showed us, that kind of illustrates different sorting algorithms. If you want like a retro 80s experience, watching some animation to learn some algorithms, that's a great place to start. Anyway, that's what I have. I think I've kind of run over on time somewhat, but I'm happy to answer questions for as long as you have them. So thanks very much.
Yeah, I have a question. Snake, thank you very much for the lecture on algorithms and data structures. How often do you use red-black trees?
Never knowingly, I guess.
Hi, I do have a question too. Thanks for the presentation. So my question was, so my journey with data structure and algorithm, at least in the beginning, they kind of stressed to you like that it's very important to kind of just focus on the worst case scenario when it comes to assessing time complexity and space complexity. But this idea of like amortized time, which is kind of like, like the average time like it takes to run this a particular operation like many times. Do you find it more useful in your line of work at like to focus more on amortized time or like worst case scenario?
That's a great question. I think, I'll give the classic engineer's answer, which is it depends. So if you're in a situation where the worst case scenario can really, have dire consequences for you, right? Like if it means you're going to run up like a big Amazon bill, or it means things are going to break down, then you really want to design defensively around that. But I worked on a problem where I was working with a stakeholder. He was proposing a solution, and I said, well, what you're talking about has like this order mn squared behavior. That's really undesirable. And he said, well, 99% of the time, n is going to be very, very small. And that sort of changed things. And then in that situation, it was better to kind of design for the expected case, knowing that a case where, we were going to have this catastrophic performance was going to be pretty rare and outside of the intended scope of the use of the system. And in the worst case was just going to make things, kind of slow for that specific user. So I would say just think about, what are the consequences of your worst case scenario? And if they're really bad for you, then design defensively, design for that. But if you're looking to create new functionality, and if the if the worst case is not something that is like world ending for you, then absolutely target the expected case.
Awesome, thank you.
Any other questions? All right, well, that's what I've got. My contact info is on this first slide. I'll send this deck to OnRamp, and again, feel free to reach out anytime with any questions that you have.
Cheers. Have a great day, everyone.
Thank you for the presentation.
Thank you.
Thank you.
Thanks.
Thank you.